Okay, Abhay, we'll start now the second lectures of Michael. And as I heard this conversation, he will start where he left. Let's see. Yeah, Michael.
Okay. So there's a natural transition between the Elisabeth's presentation and mine. If you remember yesterday, the last thing I talked about was dark matter. And so this is a different kind of dark matter than the other ones that were presented earlier. And I'll continue where Elisabeth also talked about certain approaches to try to measure axions. And this is an experiment that is being carried out right now at CERN. It's trying to measure in a penning trap, so a trap that creates an electric well and a magnetic trap for charged particles. It's trying to use this trap to measure the magnetic moment of the antiproton. So this fits into the symmetry test that I was talking about yesterday, tests of fundamental symmetries like CPT that predict or insist on the fact that particles and antiparticles have the same properties, so the same mass, the same charge, and the same magnetic moment. And measuring the magnetic moment of antiprotons is their way of testing CPT. They do this by picking up signals that are induced by the antiproton via an LC circuit, a cryogenic system that they then amplify and do a fast Fourier transform of. And the interesting thing is that this approach actually allows them to also probe interactions of any potential axions with a very strong magnetic field in which they're working. And one of the inputs to the strength or the quality factor with which one can determine axions is the temperature of this overall system. And in a way, by measuring the spin orientation or spin flips of the antiprotons, they use the antiprotons as thermometers for this whole setup. And that allows them to extract from the noise spectrum this temperature that plays a role in characterizing the effectiveness of their overall sensitivity to axions. And so what they actually would see is if there were an axion interacting with this magnetic field in their resonant cavity, they would see a spike on top of their noise spectrum. And the absence of this spike here allows them to put a limit on the existence of axions at a certain mass range. So this is what they extract out of that measurement. Here's a very wide window of axion masses that are excluded. Now, if you remember the previous talk, the axion masses can be anywhere between 10 to the minus 22 electron volts and, well, 10 to the 6 or 10 to the 7 electron volts. What they exclude is a window between 2.7906 and 2.7914 electron volts, nano electron volts, which is a very, very fine, narrow window, which means that they have extraordinary sensitivity. This is good because they can probe a coupling constant down to very low masses, but the mass range they cover is ridiculously small. In fact, if you compare this on the wider scale, between 10 to the minus 5 or so electron volts and 10 to the minus 11 electron volts, that's this very narrow needle shown here. But you can do better with the same apparatus by changing the characteristics of this LC circuit, in particular by developing superconducting tunable capacitors and laser-cooled resonators. These are the two components that are important here, but also by going to stronger magnetic fields and scanning a broader spectrum, frequency spectrum, they should be able to cover this whole range here with a sensitivity going down to here. And all of a sudden, this experiment that was doing fundamental symmetry tests now becomes a great experiment to look for axions, sort of parasitically, in addition to what they were doing all the time. Now, the problem with these windows here, you want to cover this window here, you've seen that there are ideas how to cover this area here, but the axions masses can go down to 10 to the minus 22, anywhere between 10 to the minus 11 and 10 to the minus 22. And at the same time, you've seen that to go to lower masses, you need to go to larger volumes. And at some point, you run into the problem that these volumes become impossibly large. So you have to come up with a different way of probing very, very small masses. And as was shown before, if you look at how the axions couple to electromagnetism, here's the Lagrangian, you see that there's a coupling to a vector potential. And in the presence of a magnetic field, which then transforms the axion into a photon, you end up with an effective current density that's proportional to the magnetic field. And if the magnetic field is static, then the axion current or the current produced by the axion interacting with the magnetic field will then oscillate with the same frequency as the axion field itself. And you'd like to have a resonator that resonates at that frequency. Now, the resonant cavities are possible down to about microelectron volts. Going much below that means that your volume becomes incredibly large. So how do you probe an area that you cannot probe just by going simply to bigger volumes? Well, there's been an idea that was proposed by this group here that you can try to build cavities that don't have a single resonant mode, but two resonant modes. And if the two resonant modes are slightly detuned from each other, then you have a driving pump mode, which is the first mode of the cavity, and a second signal mode, which is coupled to the pump mode through the interactions with the axion mass. And now, instead of trying to measure the axion directly, you measure the effect of the axion on the coupling between these two modes. So you've transformed the problem slightly, because now if you have a very finely tuned cavity here and a very fine-tuned cavity here, you can probe the mass difference between the two. And now you can shift the mass difference by changing the resonant frequencies. So you can start coupling very, very small masses if you can separate these two modes within a single cavity. And the way to do that, or which has been proposed, is to try to produce small perturbations in cavity geometry, which allow you to scan the resonant frequencies, the two resonant frequencies. This scan, this perturbation of a cavity geometry, modulates the frequency splitting, and that allows you then to cover very low masses with superconducting RF cavities. Now, the way that they propose to do this is by building a cavity. You have one mode here, one mode here. The difference between these two modes is the axion mass that you're trying to probe. And you're changing the resonant frequency of this device, of this cavity, by changing the geometry at the bottom of the cavity. So you're changing the size in a way. This is a little bit what's done also in higher masses, but here you really need to do very, very fine tuning, and you need to be able to separate the two modes. If you have any bleeding from the pump mode into the signal mode without the axions, obviously you're not sensitive anymore. But if this is possible, then you should be able to probe mass ranges all the way down to 10 to the minus 22, as long as you achieve a sufficiently high Q factor. And Q factors up to 10 to the 10 have already been achieved by the dark SRF collaboration. So these are sub-nanometer cavity wall displacements, really, really tiny changes of the geometry, if you can achieve that. And here you can see the sensitivity reach of these kinds of cavities then. And you can see that under very optimistic assumptions, let's say you integrate over 5 years, you have a quality factor of 10 to the 12, which is 2 orders of magnitude beyond what is already possible here. You just barely reach the QCD axion limit here. Oh, well, sorry, not the QCD axion limit, that's here. You reach the axion-like particle dark matter values. This is one way to do it. Another way to do it would be to try to change the properties of the cavity itself by working on electrical tuning of the cavity properties. And this is something that's being done right now, being prepared right now at CERN, trying to build a bimodal cavity where you can change the resonant frequencies electrically, which is probably easier to do than to tune a cavity at the nanometer scale. To go further, let me come back to this figure of merit again. How do you try to get to these other mass ranges that you would like to cover? Well, you have the magnetic field. That's one of the main parameters. The stronger the field, the better your figure of merit. The quality factor, the better the quality factor, the higher the quality factor, the bigger the figure of merit. So you can try to do these other approaches, which is to do cavity coatings to try to get to better quality factors at very strong magnetic fields. And this is really the challenge then. How do you have a very strong superconductor at fields that are as high as 11 Tesla? And this is something being worked on right now to have thin film superconducting radio frequency cavities. You can try to make multiple cavities, just repeat this stuff, build it more and more and more. Each of these cavities can couple to slightly different electric fields or slightly different resonant quality factors tuned to a specific resonant frequency, Or you can try to work with solenoidal magnets in dilution refrigerators at low temperatures. So again, this is the temperature term that is the important part here. And for that, you need to work on building cryogenic electronics, such as Josephson junction parametric amplifiers or superconducting qubit-based single photon counters. The other technology I'll quickly talk about here is atom interferometers. They're not so interesting for dark matter searches in terms of axions, but they are interesting to search for dark matter in form of ultralight dark matter or topological dark matter. And here what you're basically doing is you're probing in a way, like in a gravitational wave detector, the effect of some coupling to an external field inside an interferometer, where atom interferometers then just can be thought of here as accelerometers. So these are really just different areas that can be probed with extremely precise accelerometers. You can search for dark matter, but you can also search for symmetry violations, such as local Lorentz invariance or local positional invariance. And of course, any detector that is building on the principle of acceleration measurements can also be used as a gravitational wave detector. So what you need for these kinds of devices for a large scale atom interferometer is optical lattice clocks that are stable at precisions of about 10 to the minus 18. You need to be able to have a network, an optical fiber network operated between different metrology institutes, and you need to have developed a technique that is robust and can be run for the long term without interventions. So this is stuff you can do on Earth, but ideally you'd like to go into space with these kinds of atom interferometers. And if you do go into space, here's just a cartoon sketch in a way of what the difference between a standard electrostatic accelerometer and an atom interferometer flying around the Earth would mean if you were trying to measure the surface of the Earth. Now, this is the sensitivity of an accelerometer, an electrostatic accelerometer. And here's the kind of picture you would get. This is the equivalent water height in centimeters. And because you can't read the scale, I can barely read it. This is 0 centimeters, this is 30 centimeters. So what you can image with an electrostatic accelerometer is currently around 30 centimeters. You can tell the difference between this and this. Waves can show up, but only large waves, large structures. Whereas with an atom interferometer, you get a factor of about a 10, an order of magnitude improvement, which means you can go down to centimeter scale sensitivity. You can tell the difference between an object being here and here. And with that kind of device in space, if you build a big enough device, you can start being sensitive also again to dark matter, to couplings of dark matter, to ultralight, a scalar ultralight dark matter, to photons or to electrons. And this is what you get when you're trying to just probe gravity in a way, the universality of free fall measurements that you can do currently or in the future. And the sensitivity of these kilometer scale atomic interferometers on Earth and then in space can be shown here. And you can probe dark matter masses well below the 10 to the minus 11 electron volt range that is covered by the standard axion searches. This is for the couplings to photons. This is for the couplings to electrons. But you can see that atom interferometers can reach far beyond what is currently possible with atomic clocks or universality of free fall experiments that exist. And of course, that's the idea. You want to go build these devices, and this is being done currently in many areas around the globe. MAGIS at Fermilab, ION in the UK, MIGA in France, Zyga in China, but also possibly installing some of these atom interferometers, large-scale atom interferometers, so not tabletop, but really 10, 100 meter long atom interferometers, where you need vertical shafts, and the vertical axis shafts at CERN are an ideal testing ground, in particular because these devices have to be cryogenic, they have to work in excellent vacuum, and they're very complex devices to maintain and run. Going into space also requires then testing technologies incrementally. The first stage is going to be flown in a few years, where you would just put 2 onboard atomic transition clocks in the microwave domain in orbit on the ISS. And you're really trying to then see how you can run interferometers in space. This is then the next step in around 2030, where you're then really trying to put atomic interferometers with a stability of 10 to the minus 18 into space. And then ultimately, in about 20, 30 years, satellite missions, dedicated satellite missions with widely separated atom interferometers in space. Now, the last low energy physics approach that I wanted to talk about is a challenge in a way. You know that you can detect the cosmic microwave background, but there's another signal that is equally, if maybe not more interesting, and that is the signal coming from the neutrinos produced much, much earlier at the moment of the Big Bang. These very low energy neutrinos will tell you everything that you cannot see from the cosmic microwave background, because that only appears once the universe becomes transparent several 100,000 years after the Big Bang. The neutrinos are messengers right from the moment of the Big Bang. So very interesting, but also extremely challenging, because the neutrinos are very, very cold. So these very low energy neutrinos have almost no interaction probability. What you'd like to do is measure them. You'd like to detect these low energy neutrinos. You'd like to measure their directionality so that you can see the flux coming from different areas. And you'd like to measure their energy distribution, just like you do multichromatic cosmic microwave background measurements, the energy spectrum. And one proposal has been made, this is the Ptolemy proposal, that is trying to detect, in a first step, these ultra low energy neutrinos by, for example, interacting them with tritium. So in these interactions between the neutrino and the tritium, you have the inverse beta decay. You produce helium-3 and an electron, and you need to detect these two particles in terms of the direction and their energy. And the way that this is proposed to be done is to measure the electron, this is the difficult one, by producing actually a radio frequency tracker where you measure the electromagnetic radiation emitted by the electron in a magnetic field. This is ultra low energy. It's in the microwave, and measure the energy at the end of this via a microcalorimeter where you use transition edge sensors, these superconducting to normal conducting transition sensors, to be able to measure with a precision at the sub-electron volt, the electron energies. So to be able to do this is going to be a huge challenge. It's not clear whether any of these elements that are needed are going to work. And it's not even clear whether this process is the optimal one. There are calculations that show that actually it might be better to work with heavy nuclei as a starting point for this. I just wanted to flash this because this is probably the most challenging experiment that I know of. And the developments are very, very difficult. So now I'm going to switch gears completely and start talking about high energy physics detectors and how quantum detectors can start playing a role in high energy physics detectors. And this is, of course, typically not obvious because these detectors at high energy rely on numerous interactions between the particles that you're trying to measure and the detector itself. Whereas a quantum device basically uses a single interaction. Now, there are a handful of ideas that rely on quantum devices, but rely on them rather than use them as a single quantum detector. Because they are used in terms of their properties to enhance or to permit measurements that are more difficult to achieve otherwise. And what I'll be talking about are not finished concepts. These are not things that we know will work. These are ideas that are interesting to explore. And so everything from here on is very speculative. The high energy physics detectors really focus on measuring particles at high energy. So they're trying to do things like tracking, where you want to measure hit positions, where you need to worry about material budget vertexing, timing. You'd like to go to sub-nanosecond and ideally picosecond timing for particle identification. In calorimetry, you'd like to know the shower shape, timing, granularity of the showers. You want to do particle flow. You want to have multiple independent modes of measurement to have redundancy for every measurement to improve your knowledge. You'd like to have novel observables, things that you cannot measure right now, like helicity or polarizations, or at least not easily. And you have to worry about power budgets, event rates, and pileup. So these are the kinds of challenges that you're facing when you build a high energy physics And I'd like to show a few examples of where quantum sensors or quantum devices can help mitigate some of these challenges. And I'll be looking into 4 different areas of technology. Metamaterials, low-dimensional materials. So metamaterials are basically materials that you'd engineer at the atomic scale. And here I'll be talking mainly about quantum dots and nanolayers, talking about ultra-fast scintillators based on so-called perovskites. These are quantum dots. The concept of chromatic calorimetry with quantum dots, the concept of active scintillators, and the use of graphene in gas electron multipliers. Then I'll also be talking about the role that atoms, molecules, and ions can play in detectors by talking about the concept of Rydberg time projection chambers. I'll show how you might be able to build a helicity detector, a particle helicity detector, by using spin-based sensors. And I'll talk about detecting dark matter candidates, or almost dark matter candidates, with superconducting sensors. So let me start with the first area. And here really the most important aspect of quantum dots is that they're very fast. They are very small. They have a few nanometer size. So light is produced rapidly and emitted very rapidly. And you can see that if you excite a nanodot, so this is basically a crystal composed of a few hundred atoms, or composed of composite atoms of cesium lead bromide. If you excite this nanodot, it has a natural fluorescence decay time constant of, well, sub-nanoseconds in any case. There are several components to this. One of them has 43 picosecond time constant, decays very rapidly. Another one has 350 picosecond time constant. So these are very rapid scintillators, and that's exactly the kind of thing you want to have if you're trying to measure when light is emitted by a particle passing through, so that you can tell, for example, the time of flight of a particle on a macroscopic scale. This is not a characteristic only of this particular composition. The same happens for this kind of nanodot, ZNO gallium, which also has a photoluminescence decay with a time constant of less than a nanosecond. So this is, in this case, 210 picoseconds. These are extremely rapid scintillators, very interesting from that point of view. But the question is how much light they produce. So one has to think about whether the integrated light yield that you need to be able to measure this rise or this decay is sufficient, whether you need an impossibly large density of these nanodots. Now, that's something where, I'll come back to this afterwards, but where one has to think about how useful this concept can be. But there's another aspect of nanodots that is definitely going to be useful, and that's the fact that depending on the size of the nanodot, the emitted light is going to be of a different color. Nanodots that are very small emit mainly in the blue. Nanodots that are very large emit mainly in the red. So you can really get a chromatic sensitivity of your scintillator by just choosing the size of these nanocrystals. This chromatic tunability allows you to optimize, if you coat your scintillator, for the quantum efficiency of the photodetector. And this basically means that your quantum nanodots can be used as fast, optimizable wavelength shifters. Typically, you put a wavelength shifter at the end of a scintillator, just in front of the photodetector. So you might deposit these nanodots on the surface of a high Z material, and produce a thin layer. And in these thin layers, you transform the UV light that is produced by the charged particles going through the scintillator into visible light. But you might also think of embedding these nanodots inside the scintillator itself. For example, via 2 species, nanodots and microcrystals of high Z material with scintillators inside a polymer matrix, which means you get a quasi-continuous visible light emitter calorimeter. Now, let me take that idea one step further. Depending not only on the size of the nanodots, but also on their geometry, the spectrum of the emitted light, so in these triangular carbon nanodots, the spectrum of the emitted light suddenly turns out to be extremely narrow. You get, in these specific cases, emission spectra that have a full width of 20 nanometers, which means that between the emission and the absorption spectra, there's no overlap, which means that once a photon has been emitted by the nanodot, it can no longer be absorbed by another nanodot of the same type. These two dots mean that I can only absorb UV light for these very small nanodots, which is then emitted at a lower frequency, a higher wavelength. And that higher wavelength then will go through the rest of the nanodots, which for them is completely transparent. By choosing different nanodots of different geometry and different sizes, I can choose which wavelength I end up with. And that means that I can take the next step with this, which is to build a device which consists of multiple layers here, seeded with nanodots of different sizes, each of which will emit light at a specific color. So UV light produced by incoming particles entering this part of the colorimeter and starting to form a shower, this red light will be transparently transmitted right until the end of the colorimeter. The same happens for the red light here, the yellow, the green, the blue, and the violet light. And all this light is then measured at the end of the colorimeter via a spectrometer, which measures the spectral intensity of the light. And that spectral intensity tells you how much light was produced here, 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 here. And from that spectral intensity, you can then reconstruct the shower profile in the depth profile of the shower produced by the incoming charged particle. This is something that is very nice to have in terms of calorimetry at high energies. How well this works will depend on how well you can build these nanodots, so how narrow these will be, how large a spectrum you can cover. So here we can cover a spectrum going between 400 nanometer emission all the way up to 700 nanometer emission, and how many layers you can build in a way, how well you can separate this. And typically with nanodots that are currently already available, you should be able to segment this into 10, 12, 16 layers, more or less, which is sufficient to get a full depth profile of the shower profile here. Of course, that's the nice part. The hard part is then building the spectrometer and measuring the spectral intensity. For that, you need to think about how you can separate the light that's produced at the end of the crystal into its different frequencies and how you then detect the intensity of each different frequency. And this is an area where, for example, metamaterials can start playing a role because you can build very thin layer optics by carefully building structures on the surface of this area at the end of the scintillating crystal. This is just standard emitters. They don't do anything smart. They just fluoresce as you trigger them, as you illuminate them with UV light. They're passive. You cannot amplify them. You cannot turn them off or on, and they can't be modified once they're in place. So these are things that are, well, nice, but you can go further. And going further would mean, for example, thinking about having active scintillating materials, materials where you can electronically amplify and modulate their response to incoming radiation, which you can turn off or on, pulse and prime for collisions. Or we can adapt the gain in situ to react, for example, to aging effects, where the light that is emitted is less intense as a function of time. And these kinds of active scintillating materials exist. They're quantum dots that are built in bulk, for example, by mixing in different compositions, gallium arsenide and indium arsenide. You can control the growth, the natural growth. These happen without having to be built intentionally, of quantum dots, quantum well dots, and quantum wells. And the emission spectra of these different structures depends on the type of structure that you have. So the quantum wells here emit in the near infrared, the quantum well dots a little bit longer wavelength, the quantum dots in the mid-infrared. Their time constant is also very different. The quantum wells fluoresce on a very slow time constant of almost microseconds, whereas the quantum dots have time constants of the order of nanoseconds. So these are the ones you should be focusing on. You could build these, except that they emit in the infrared. Now, this could be a drawback because our optics are currently built to detect visible light. But it's interesting to note that silicon is transparent at these wavelengths. It's completely transparent. This is where the whole telecommunications industry is working. The fibers, the glass fibers, actually work in the far infrared. So one could think of even transporting scintillating light through a silicon-based tracker to further outside photodetectors. And furthermore, putting quantum dots close to the beam pipe rather than having your scintillator outside of the tracker is perhaps made possible by the fact that quantum dots are radiation resistant. At least these types of quantum dots are radiation resistant. Of course, one needs to study this to see exactly how radiation resistant they are. But this kind of approach might lead to turning the current concept of having very little material tracking detectors on the inside and heavy material calorimeters on the outside on its head. These quantum dots are very narrow band, so you can get rid of a lot of background. If you think of how these gates work, you basically accumulate electrons. You have a voltage then here, which stops the electrons from falling into your well. And you can, with a voltage pulse, change this voltage step into a zero voltage. So any electrons that are accumulated here will fall in, which means you can set up the time when you see the photon signal. And by choosing the well depth, you can tune the emission spectrum itself. So you get very narrow, almost atom-like emission pulses, fluorescence pulses or light emission. And that helps you reduce any background that you might have otherwise. And these are still just the standard quantum dots that exist. Now let's take this concept one step further. In a silicon detector, as a particle goes through it, it releases a large number of electrons. And you'd like to measure this signal. Normally you do that by just collecting them on an electrode. But I'd like to introduce the idea of coupling this kind of device with another kind of device, which works with a single electron. This is a single electron device where you have an electron enter a quantum well region. And as it tunnels through this barrier, it loses energy because this well is lower than this well. And it emits the energy difference between this well and this well in form of a photon. Now, if you stack these wells one after the other, as the electron tunnels from layer to layer, it will emit photon, 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 photon. All these photons have exactly the same energy that are by construction equal in wavelength. This is a quantum well cascade laser. And it's interesting to think about the potential that one would get if one could couple these electrons here, which are hundreds of thousands of electrons, to a quantum cascade laser, which emits many photons for each electron. If you can do that, then you basically multiply the number of photons that you get out of this by the number of electrons that you have here. Furthermore, this emitted light is monochromatic and tunable in the range of 3 micron to 12 microns. So you can choose where you're particularly sensitive. But this light is in the infrared. It's in the terahertz, which of course is a very active area right now, which means that if you're thinking about building a quantum cascade laser amplified electron counter, then you need to have the electronics that is able to detect these photons and count them very precisely. And then finally, you can actually think about embedding everything into a single structure, which has both the photon emitter and the photon detector in a single compact package, as does the dot-pix approach, where you have these indium arsenide or gallium arsenide quantum dots. These are the scintillators. They emit photons. And immediately after that, you have a photodetector array, a pixelated photodetector array, which means that any light that you pick up here tells you the position of the scintillator, of where the particle interacted with your detector. So this is now optical tracking of where the particle went through your detector. And this can work as long as you get enough infrared light emitted from these quantum dots. Now, just to reassure you, if you look at the emission spectra or the emission in the light yield of different scintillators that are known for different decay times, so this is the inverse scale, the further to the right, the faster you are, then the current scintillators that are being used, LiSO, lanthanum bromide, BGO, these are scintillators that people use currently. The more recent ones or more the rapid ones like barium fluoride or lithium barium fluoride are down here. Lead tungstate is down here. These indium arsenide quantum dots are up here. So they are both very bright and very fast. And there's a good chance, people are working on increasing the light yield, of going up to this point here, which would be the brightest scintillator that exists, at the same time being the fastest scintillator that exists. So these quantum dots have enormous potential as being very rapid and very bright scintillators. From zero-dimensional materials to two-dimensional materials, this is an activity happening right now at CERN, where monolayers of graphene are being studied with two applications in mind. The first one is inside a drift chamber, where one has a detection volume where a charged particle flying through the gas will ionize the gas and produce electrons that then drift into an amplification region. And in this amplification region, the electrons are multiplied to such a point that you can detect them. The ions that are produced in the amplification regions will drift back into the original detection volume and poison that area, because any positively charged ion will absorb any electrons that are produced by charged particles. And so you have to stop these ions from getting into the drift volume. And this can be done by building a sort of one-way gate, which is transparent for electrons, but not for ions. The graphene layer, the monolayers of graphene, should play such a role. Their openings inside the graphene monolayer are so small that ions cannot drift through, but electrons, as has been shown in this experiment here, can travel through with a transparency of up to 99.9%. So this is a very efficient filter that stops the backflow of ions into the detection region if you can build monolayers of graphene and spread them over a very large area. The same monolayer of graphene can also be used to tune the work function of the photocathode that is used to then detect the shower. You can see here the effect of monolayers of graphene, one monolayer, two monolayers, three monolayers, four monolayers, on the work function of this photocathode. And you can see that for a few monolayers, this allows you to tune very precisely the exact value of the work function. Now, these are things that are happening right now in terms of these low dimensionality materials. Let me come to the role that manipulating atoms can play in high energy physics detectors. Now, this is again the same kind of detector, a time projection chamber. So this is a very large drift volume in which you detect particles that are produced, for example, in the interaction of two protons. As these secondary particles fly through the TPC, they ionize the gas. The electrons that are liberated by the ionization drift towards the amplification region. And in here, the electric field between this plane and this plane produces the showers that you want to see and detect. Now, right now, you live off the fact that an electron, as you accelerate it, has an interaction with the gas in here and ionizes that gas, produces more electrons. But what if before this electron enters here, you were able to excite the atoms in this amplification region into a Rydberg state, which means that the ionization energy needed to ionize them completely is much lower than if the electrons are in the ground state. That's the idea of this concept here, is to pump the atoms in here into a Rydberg state just before the electrons arrive. So this works for a high repetition rate, but not very high repetition rate detector, like in the Alice experiment, and to use the fact that you would then get more electrons liberated for the same amplification voltage here than you would get normally, because the ionization energy is lower now. So this means you can either have more electrons, better signal to noise ratio, or you can work with a lower voltage. For the same amount of signal, you need less voltage to accelerate the electrons because they will ionize anyhow. And so that means that you produce less ions and that you get less drift back into the original region. So those are the two possibilities that you would get. And you can play this game even further by acting on the drift volume itself, by exciting the atoms in here to a low-lying excited state. As the interaction happens and the particles fly through, the interaction between the particle and these low-lying excited atoms will increase the excitation level of the electrons in the atoms and ionize a few. And then right after that passage, you shoot a laser into this volume again and photoionize any highly excited atoms. So you get more electrons per charged particle flying through than you would otherwise get. Which means you can use different gases, gases that are less sensitive, or you have to worry less about poisoning of this volume here through backflow of ions. The next topic I'd like to quickly cover or address has to do with helicity detection. So I've mentioned that you can build spin sensors, for example, through nitrogen vacancy diamonds, where within the crystal lattice of a diamond, you have individual nitrogen atoms whose energy levels are going to be very precisely sensitive to any external magnetic field. So you can probe their state optically and measure the magnetic field surrounding them optically. But you can also turn this on its head, as been done by this group here, which uses the fact that you can manipulate these vacancies with microwaves to polarize them, and then use the fact that if you polarize this atom here with a laser and microwaves, then the surrounding atoms will also be polarized. So you can obtain hyperpolarization in the vicinity of a vacancy, which covers something like 100 times atoms more than the ones that are in the vacancies. This kind of hyperpolarization allows you to polarize the surface of the diamonds. And in this particular application, molecules which interact with the surface of these polarized diamonds then become spin polarized themselves. And you can use this to produce spin polarized marker molecules. Now, let's take this idea one step further and build devices which are not only partially polarized, but fully polarized. So you have 100 atoms per vacancy. You have about 10 to the 16 to 10 to the 18 vacancies per cubic centimeter. So you're covering about 10 to the 20 atoms among the 10 to the 23 atoms that are polarized. Let's assume for a moment that we can gain another factor of 1,000. So just increase this by a factor of 10 in every dimension, so that you have a bulk polarized monolayer of nitrogen vacancy diamonds. In these monolayers, these polarized monolayers, a charged particle will scatter, but the scattering will depend on the orientation of the particle's helicity with respect to the polarization of the plane here. And if you do this in multiple scatterings, which you measure through a series of position-sensitive detectors, like the silicon detectors that are part of the high-energy physics trackers, then you can build from the multiple scattering a probability distribution that tells you what the likeliest helicity value of the particle coming in was. This allows you to build something that would be a helicity tracker. Right now, if you want to know the helicity of a particle, you need to work on the decay of that particle. You need to see how that particle decays and measure the angular distribution of the particles, of the decay particles, relative to the direction of the initial particle. If that particle doesn't decay, you cannot measure its helicity. This would be a possibility to perhaps measure its helicity for every charged particle that comes in. Of course, it requires R&D to go beyond what is currently possible, but it doesn't seem inherently impossible to build this kind of thing. And the last detector I'd like to quickly talk about is the use of superconducting detectors for charged particles, but for a specific type of charged particle. So if you look at what these superconducting detectors do, and for example, in the case of superconducting nanowire single photon detectors, what they do is you have a superconducting state, a photon interacts with this state, heats up locally the superconductor, creates a domain which expands, cools, and goes back to superconducting again. So this transition here can be seen as a voltage pulse at which these different moments in time are indicated. And this voltage pulse allows you to detect the absorption of a photon by these superconducting nanowires. But of course, the same thing will happen also if instead of a photon, you have a charged particle going through this detector. It will heat up, produce a voltage pulse, and so on. Now, the interesting thing is that these detectors are extremely sensitive. They have a sensitivity currently at the level of 100 millielectron volts for a 10 micron thick detector. And in a few years, that sensitivity should go down by 2 orders of magnitude to around 12 millielectron volts for a 100 micron thick detector. Now, that value, 12 millielectron volts for 100 micron, has to be compared to what a minimum ionizing particle deposits inside a normal detector, which is 20 kilo electron volts per 100 micron. Now, this is a factor of 1 million more sensitivity, which means that if you have an apparatus that is this sensitive, you will definitely see every minimum ionizing particle, but you should also be able to see particles that deposit less than the minimum ionization signal that a MIP will deposit. Milli-charged particles, particles that have a thousandth or a millionth of a normal particle charge, would become visible at this level, although, of course, they will never deposit this amount of energy in the detectors that are currently being used. So if you're looking for milli-charged particles, you could build a device like this, where you have a stack of these pixelated devices, where a normal minimum ionizing charge particle will pass through and produce signals, basically just telling you 0 or 1. There is a hit or there's no hit. And you can veto these particles by putting a veto shield or a muon shield around this device. But a milli-charged particle will pass through the muon shield without leaving a signal because it is not sensitive enough, but will fire the pixels inside this TS stack. So what you've basically built by stacking an array, a stack of different arrays of transition edge sensors on top of each other, is a tracker for milli-charged particles. Has to work at cryogenic temperatures and so on, but this could very well be placed inside a larger experiment positioned at a beam dump, where you produce vast amounts of secondary particles, and the only background you have to worry about are the muons, the minimum ionizing muons. This would be a very sensitive detector for milli-charged particles, down to a charge of around 1 millionth of an electron charge. And the current limit for milli-charged particles is around hundredth of an electron charge. So this opens up several orders of magnitude further sensitivity. And you can think of using the same kind of structure also in a different way, because these are very small, thin layers of detectors. They have 10 nanometer layers. This same stack should allow you to differentiate a charged particle that is produced here and that flies through from a neutral particle that flies through several layers of the stack and then decays. The path length here can be down to something like 100 nanometers. So neutrals that have very, very short lifetimes could be detected directly this way if you shoot a primary beam into the same kind of stack. Now, whether these kinds of particles exist or whether they're relevant, that's a different question. But the detector itself could be built and maybe probe further phase space. And I think with that, I just have 2 summary slides to give you. These are the families of quantum sensors that are currently being looked at. This is where we are right now. These are the goals where we'd like to be in 5, 10, 15, 20 years. And the idea is to have devices that produce functional high-energy physics detectors by around 2040, so in about 20 years. And the size of these dots tells you something about how unlikely it is to get there or how much work is going to be needed. The further into the future, the more work is going to be needed. But already now there are activities working on several of the goals that are very, very ambitious. And this overall effort of trying to develop quantum sensors as detectors for particle physics experiments in the future has now started and will gather steam in the coming years. And hopefully we'll be able to build devices based on some of these ideas or many of the other ideas that hopefully will still come by the time that they might be used. And this is useful, of course, not just for low energy physics, low energy particle physics, but also for high energy particle physics, as I hope I've shown you. And with that, I've come to the end of this talk. Thank you.
Okay. Okay. Before asking the question, okay, first of all, thanks, Michael, for this very excellent talk. I just add one more point. You know that now neutrino physics, neutrino oscillation, it is the well-known subject. But when Ray Davis shows this result almost 25 years, no physicist believed it. Physicists said, oh, this is the chemistry, this is not our field. And even nobody tried to do that experiment in physics-wise. That was a completely different field. And this quantum sensor or what is she showed, these are the completely new things. Many things might come up from here. Yeah. Okay. Thanks. Now
if you could walk us through the motivation of the optical tracker, I'm missing something there. So is the idea to have, let's say, a EM calorimeter tracker merged into one within the solenoid, for instance?
Well, in a way, what you would do with this is you replace the standard pixel detectors with optical trackers, with an optical emitter that's also pixelated. The advantage here is that you get extremely fast times. Remember, the quantum dots give you sub-nanosecond time constants. And as long as your electronics can follow, you should be able to do a tracker, high-resolution tracker, which is also high resolution in time, which means that you don't only just do spatial tracking, you also do temporal tracking, which means you do time of flight measurements to differentiate particles from each other or to mitigate pileup. That's sort of the idea behind this kind of thing. And the fact that they're bright enough means that this will probably be a feasible alternative to, for example, having a standard tracker and two timing layers. So redundancy, complementarity, that's all the game here.
Got you. It's replacing the timing layer.
Okay.
Sir, so my question is related to the superconducting on the slide 63 you showed. So if the charged particle is locally increasing the temperature and the medium is getting out of superconducting state, does that mean that the detector has to work just below the superconducting temperature?
Yes. Yes. So these transitions here, you're really sitting on a curve that looks like this. So you have a cold, actually it's pretty much this. You have a cold state that is sitting on just below the transition to normal conductivity, and a tiny energy deposit just pushes it over the threshold. So you really live off the sharpness or the steepness of that edge. Yes.
And I have one more question on slide 53, where you showed the laser cascade. So there are lots of IR photons getting released. So is it not possible that these might get absorbed in the medium itself, exciting the vibrational states? Or
absolutely. So this is where you have to think about how the geometry of that device can be matched. Normally, when you look at these quantum cascade lasers, they have an open face like this, so that these low energy photons come out, well, like this, out of the plane. So you have to think about how to orient your device in such a way that it would be possible that the photons are no longer reabsorbed. For example, by putting your photodetector right on that plane, that might be a way to deal with it.
Thank you. Thank you.
Any more questions? Okay. Then this is just again the same things, Michael. Again, this is from the institute.
Thank you very much. This is something I look forward to. I look forward to reading this, to having a look at it.
Yeah, also this one.
And thank you again.
This is
nice. Okay. I'm painted, yes. So I just noted how things have changed since 30 years ago. This guy up here, it would be completely impossible these days, right? No smoking.
No, but that was actually, it is a 54 or something. It was 54.
Yeah, but you can't do that anymore.